Hello, everyone, and congratulations for surviving a semester of PChem 2 in what may be the weirdest semester of the year. So, today we're going to be wrapping up our conversation on spectroscopy, talking about an entirely new way of doing spectroscopy. So, this is going to be Raman spec, and hopefully, I'll not make a soup of it. So, Raman spectroscopy differs immensely from traditional absorption spectroscopy. So for absorption spectroscopy, a photon comes in, excites my molecule to some new state. I measure how much of the light is absorbed. Congratulations, we can figure out, based on the radiation of absorption, where the difference in energy in between two states. Raman spectroscopy works by a very different process. So for Raman spec, instead of scanning through a whole bunch of wavelengths, I'm going to typically use a single wavelength of light where I will then where I can then excite my system to some very elevated state. So this is a much higher energy incident radiation. And then what's going to happen is it will immediately collapse back down to another state. So one of the things that makes this quite different is instead of light being absorbed and then emitted, like classic emission spectroscopy, instead this process is actually fairly quick. And so visually what you tend to see is light almost being scattered outside of the molecule as the new radiation will spin off in some new direction. This is further complicated by the fact that the wavelength of light emitted doesn't necessarily have to be the same as the wavelength of light absorbed. And this is actually one of the biggest strengths of Raman spectroscopy, and it allows us to break down our Raman peaks into three different classes. So I'm going to be talking about this a lot throughout the lecture, but our three classes of radiation are going to be the anti-Stokes peaks. So this is where my molecule relaxes to some lower energy state. Now, it is worth noting that while I go from, say, state J to J minus 1, this means my molecule is going to relax in energy, but it also means that the photon that I emit or scatter is going to be of higher energy than the one absorbed. And so a good idea of what's happening is that I stole some energy from the molecule to turn it into that extra energy in the emitted photon. We then also have the Rayleigh peaks, which is traditionally referred to as Rayleigh scattering. So this is where I excite the molecule and then immediately relax back down to the same state. So in this case, the energy of the light scattered is going to be the same as the energy of the light absorbed. And then finally, we have the Stokes peaks. So in this case, I excite into my elevated state and I don't quite make it all the way back down to my original state. I get lazy and I stop at some higher energy state. So this is actually one of the confusing parts about Raman spectroscopy. Anti-Stokes peaks are relaxed to a lower energy state, which gives me higher energy radiation. Stokes are relaxed to a higher energy peak, which gives me lower energy radiation. And this kind of inverse relationship is one of the trickier ideas of Raman spec. Now, what's kind of cool about Raman spectroscopy is this is a general technique, and we can apply it to a lot of the regions that we've previously talked about. So let's start with rotational spectroscopy. It's a great case. And one of the most useful parts about Raman spectroscopy is that it turns out that it obeys slightly different selection rules than traditional rotational spectroscopy. So if I'm doing a classic microwave spectra, turns out that I can only rotationally excite molecules that are polar. Turns out rotational Raman doesn't have that same constraint. I can actually excite non-polar molecules, but what I rely on is the fact that the molecule has to be what's called anisotropically polarizable. And this is essentially a fancy way of saying that I have to be polarizable in one direction. So this is generally a way of thinking about, let's say I A rotational peak is going to be allowed if essentially when I rotate the molecule, instead of changing the polarization, what I do is I change the polarizability, but again, only in one direction. So what ends up happening is if I say have a linear molecule and I end up speeding up its rotation along one axis, this is going to elongate out the density of the molecule. And the more elongated out the density is, the more easy it is to polarize the molecule. Because again, this is something that you may have seen in general or organic chemistry. The polarizability is largely driven by how diffuse the electrons are. Now, turns out if you try and apply this same, and so we can see is for rotational states, for linear molecules, we can apply this these selection rules, and we find out we get specific selection rules of what excitations are allowed. That my rotational state is, of course, allowed to not change. This isn't going to be a big deal for pure rotational spectroscopy, but will come into importance later when you couple it to vibrational spectroscopy, just like we did for absorption infrared. But we also can allow the rotational state to increase or decrease by 2. So again, this is going, both of these cases will actually be allowed for rotational Raman, because for a rotational spectra, I am occupying multiple different J states, which means that my J state can go up or down. And unlike absorption spectroscopy, where I'm putting energy into the system, so it has to go up, in this case, what I'm measuring is the amount of light emitted when I fall back down to this state, to my final state, which does actually allow for pure rotational Raman spectra to actually give us a decrease in our J value, which again is a big advantage uh, from what we saw for traditional microwave spectroscopy. Now, however, it does turn out that this anisotropy component is actually quite significant when we're talking about spherical rotors. So this would include things like perfect tetrahedrons or octahedrons. So so molecules that belong in the TD or OH group. Because these molecules, due to their more spherical nature, any polarizability that you get from speeding up the molecule tends to be more evenly distributed. So these will still tend to be Raman silent. However, we can actually perform Raman spectroscopy on symmetric molecules. However, again, it's worth noting that the more symmetric axis, so the parallel axis, the one that tends to be the most symmetrical around the middle, this actually can't change states. But instead, we can actually see excitation or depression in the overall rotational of the states of the other directions. So for symmetric rotors, it is worth noting that linear rotors, I have to increase or decrease by 2. Symmetric rotors, turns out we can get around that a little bit, and we can have increases or decreases by 1 or 2, or again, no change. This will be your Rayleigh peaks, increase will be your Stokes peaks, and the decrease will be your anti-Stokes peaks. So let's go ahead and take a look at a real rotational spectroscopic signal and kind of see what it looks like. So I can go ahead and perform a rotational spectroscopy signal, and the most pronounced peak that we'll probably see is going to be right here in the middle, and that's that Rayleigh line. And this will be centered about VI, where VI is the wave number of the initial incident radiation. So this will tend to be our largest peak, first of all, because it doesn't matter what J state I started in. This just shows that no J change was observed. So that in and of itself is going to significantly increase the height of the Rayleigh peak. As well as you can run into some difficulties of this being the frequency of the original incident light. Though usually the setup of Raman spectroscopy, of a Raman spectrophotometer can usually depress the incident rate, the observation of the incident radiation. However, we still have to worry about the Stokes and the anti-Stokes line. So let's go ahead and start with this idea of the Stokes line. So at this point, what I'm going to be interested in is the wave number of the transition from state J to J over 2. So this is essentially where I'll start, say at state J, I'll jump way up, and then when I fall back down, I'm measuring the light of when I fall to that increased state. So again, my rate, my observed peak should be centered on the location of my incident light. But what I'm really going to be caring about is how much shorter I fell of that radiation. So of my incident radiation, how much energy did I steal from that photon in order to increase my rotational state? And that's going to be based on the rotational energy difference of the J plus 2 and the J state. And so what we'll find is that we will be slightly lower in energy, or sorry, lower in energy, which means slightly higher in frequency. Slightly lower in energy, which is lower wave number, lower frequency than our initial incident light. And this will show a J dependence because again, remember our rotational states, the difference does significantly increase based the difference in energies between our states significantly increases as we go to higher J's. And again, we see this with the Raman spec in the same way we did for our traditional rotational spectroscopy. So again, what we'll see is that we'll see peaks for low initial J values near the Rayleigh line. And as we get further and further away, we will have higher and higher J states. And this difference will be related by this difference factor, the 2J plus 3, but it's also going to be largely driven by the rotational constant, which again, largely tells me a lot about the moment of inertia of the molecule, which, as you've seen in lab, can be used to backtrack things like bond lengths. However, we have a whole nother set of peaks that we are often concerned with, and these are anti-Stokes lines, and they'll be given by a similar expression, which will focus on a similar phenomena, which is going to be how much energy, the energy difference in between my initial J state and the J state two quantum levels lower. And so by taking the difference of these two states, we start at J, we go down to some lower frequency. This extra energy gets imparted to the photon that's emitted. And again, this difference will have a dependency upon what rotational state was originally occupied and the moment of inertia of the molecule. And again, one of the things that's important to note is just like for rotational spectroscopy, most of our peak intensities are largely going to be reflective of the occupation of each J state. For low J states, these are energetically favorable, but have low degeneracies, so there aren't many free spots to occupy. By the time we get to high J states, these have large degeneracy levels, so there's lots of different states that we can occupy, but unfortunately, it turns out that they're all fairly high in energy. So again, we tend to see dominant peak intensities at some intermediate J level. While typically our Stokes lines will be slightly more intense than our anti-Stokes lines, simply because our Stokes lines tend to reflect lower J values than our anti-Stokes who are falling down. So for example, there will be no 0 or 1 J value for our anti-Stokes lines. And that is something to watch out for. Now, this essentially is fairly analogous to what we saw for traditional rotational spectroscopy, but we can extend these same ideas to vibrational spectroscopy, where again, biggest difference in between vibrational and Raman spectroscopy is for vibrational spectroscopy, the molecule must change dipole along the axis of vibration in order to be active. Turns out for Raman spectroscopy, all that's required is that the molecule must change polarizability as it vibrates, and we'll talk about that a little bit more later. But there's also another important difference that in between our vibrational Raman spectroscopy and our rotational Raman spectroscopy. Because in rotational Raman, we are often occupying J equals 1, 2, 3, 4, 5 states. It turns out for vibrational Raman, we're pretty much just in the V equals 0 state, which means I can't go any lower. So you tend to not frequently see anti-Stokes lines for vibrational Raman spectroscopy. But it turns out that my vibrational states are still going to be linked to my rotational states. So a lot of the analysis of vibrational Raman is actually going to be focused in on vibrational rotational coupling. And so we can take our vibrational Stokes lines and still split them into 3 different branches. So these are going to be quite analogous to my Stokes and anti-Stokes lines, but to make sure we don't confuse them with the vibrational levels, we're going to use slightly different language. So the first of which is going to be the O branch. So this is going to be related to the anti-Stokes lines, where my rotational state will drop by 2. So I'd say go from the J equals 2 to J equals 0 state. So these will all be lower in these will all be higher in energy than my original Q branch, which represents essentially the same thing as our Rayleigh line. So our J branch exhibits no change in the rotational state. So this means that all change occurs simply through the vibrational state. As a consequence, this tends to be the largest peak simply because it includes all possible J values. And then finally, we have the S branch. This is going to be related to the Stokes case. So these are all going to be higher in energy or all lower in energy as I'm going way up and then coming back down to the J plus 2 state. So this means that some of that energy got, which means that I stole some energy from the original photon I absorbed, and the photon released will have a lower energy as a consequence. Now, again, we tend to care a little bit more about what the energies or peak locations of each of these species will be. So we can analyze each of these branches to determine the appropriate peak locations. So let's go ahead and start with the O branch. So again, these are going to be the same thing as the anti-Stokes peaks, where I am falling down in energy. And as a consequence, what we end up finding is that since I'm going to have the wave number of the light that I observe is going to be, of course, related to the incident light. And I stole some energy in order to excite to a higher vibrational level, which according to the harmonic oscillator should differ by the rotational constant. But I stole some energy back from the from the J states, which will end up shifting me in a positive direction, again, based on the rotational constant. So again, this should be this extra term should be quite analogous to what we saw for rotational spectroscopy with some small variations. We then have the Q branch, which again shows no changes in J states, which will then result in its higher intensity. And as a consequence, it is at a static location, as it will simply differ from my incident radiation based on the vibrational constant, which again includes many important factors such as the stiffness of the bond or our force constant for the harmonic oscillator. So it turns out this is actually quite a nice way to using vibrational Raman to try and back out our to smoothly back out our vibrational constant. However, we also have the S branch, which is going to show a decrease in energy, because again, I stole some energy to increase both in my vibrational, but also now in my rotational states. And again, will be related based on both the vibrational and rotational constants and can have values of 0 to 4. And again, what we're going to see is one of the biggest differences in between Raman and traditional IR spectroscopy is that our Raman spectroscopy is going to allow for the measurement of nonpolar linear molecules. So these are molecules that are traditionally IR silent. Because again, one of these big advantages is this difference in selection rules. Because for Raman spectroscopy, our simple rule is that the molecule must change polarizability during vibration. So let's go ahead and take a look at our V1 state for CO2. So last time we showed that for IR spec, this molecule does not change polarity as it starts nonpolar and it ends nonpolar. But it turns out that this vibration does correspond to the molecule getting bigger and smaller. And this change in how diffuse the electrons are actually ends up influencing the polarizability of the molecule. So it turns out that this V1 state, while it is IR inactive, is Raman active. So this is a good way to try and back out information about this state. And it turns out that this is going to be related to a special rule that says if a molecule has an inversion center, so in other words, if it possesses inversion symmetry, it can't be both IR and Raman active. So CO2, great case, it has inversion symmetry. Again, inversion symmetry is going to be related to often related to nonpolar molecules. So if a molecule has inversion symmetry and it is Raman IR inactive, it will be Raman active. Conversely, I have a molecule like this that is IR active, but turns out to be Raman inactive. And the general idea behind this is that both of my oxygens are moving in the same direction, which ends up meaning that I'm not so much changing how diffuse my density is, more just moving the location of that density all slightly to the right. And you see something very similar with these V3 states, where all I did was just slightly move the density instead of widening it or shrinking it. So we see a very opposite trend that we did for IR spectroscopy. So for IR, V1 was inactive, V2, 3, and 4 were active. For Raman, V1 is active, V2, 3, and 4 are inactive. But it turns out that with water does not contain an inversion symmetry. So this rule does not apply. And instead, what we can then again is look at this polarizability. So what we end up finding is for this V1 symmetry, the molecule is more or less shrinking in size, which means it will be less polarizable. For V2, it turns out that this is actually going to net increase the size of the molecule, so it's going to be slightly more polarizable. And it turns out because of the uneven size for V3 of the oxygens and hydrogens, it turns out that V3 becomes slightly more polarizable. So it turns out that all three of these signals will also be Raman active as well as IR active. Though it is worth noting that we will see reduced signal strength, which whereas for infrared spectroscopy, water tends to obliterate any opportunity to get signals in these regions. It isn't quite so bad for Raman spectra, so it is still possible to use water as a solvent. So this should hopefully give a quick crash course into Raman spectroscopy. It's a little bit more of an infrequent technique, but still has a lot of use. Unfortunately, due to the fact we are measuring scattering instead of original absorption or emission, it tends to mean that Raman spectrophotometers are a little bit more expensive, thus the fact that it's used a little bit more rarely, while it still ends up providing a lot of very useful information. So, I want to thank everyone for bearing with me. You made it through all the lectures. Take care, stay healthy, and let me know if you have any questions. Have a good summer.